Hello everybody, I'm going to talk right now about integrated rate laws. We'll do a couple videos on this because it's relatively, I don't say complicated, but it's a process that will involve a few steps. We're going to do this for several orders of reaction types. So we're going to look at generally reactions in the form of, we'll keep it really simple, of just some species A, doesn't matter what it is, going to a product of products. And what happens is, so here we just have something A to products. If we were dealing with, I'll deal with the first order case first. And let me just say this as a prelude, is that the results that I'm going to present here do involve calculus. I'm not going to use calculus because this is an algebra-based course, not a calculus-based course. But if you do know calculus, you can certainly refer to the back of my skill builder. I have a little appendix or whatever you want to call it. That's kind of FYI that shows the derivation of some of these explicitly. So a first order process, we would have something in the form of rate. I'll just call rate R is equal to K with A to the first power. We don't show a 1, but it's implicit that it's 1. That's going to be equal to, that's a reactant, the change in the concentration of A over the change in time. Now, if you know calculus, you could write this as a derivative, negative dA dt. And when you solve that type of equation, you can get it in the form as this. This is the natural log ln, the concentration of A, and I'm going to put a little subscript here, meaning at time t, you're recognizing that A is a function of t. So A here, the concentration of A is a function of time. So I'm just using a notation just to make that clear. I'm putting a little subscript t there. It's really not important. And compared to A naught, and the zero or the not symbol, little zero symbol, just represents that that's at the beginning of the reaction, which I'm going to always define the time equals 0. That just seems convenient. And so that's going to be equal to negative K, the rate constant, times time itself. That is one of the solutions of what we call an integrated rate law. And it's absolutely good form for doing a lot of calculations. Sometimes you want to show the results of a first order process graphically. We want to draw a straight line because remember before when we're plotting concentration versus time, it wasn't usually often it was often not a straight line. So if we expand this out logarithmically, we can write this as ln of A sub t. Again, A is a function of time is equal to ln of the concentration of A sub naught, the initial concentration will be some number, minus kt. This is the equation of a line. Remember, equation of a line from high school math, y equals mx plus b. So here, this would be your y. This would be your intercept m. And then this here term is your x, is your mx. So very important here is that the slope, what often in algebra is called m, is equal to negative k. The rate constant will always be a positive number. So how do we interpret this is, let me erase a little bit, or I could use this side of the board over here. What we have is, if we plot this as ln of AT, as the y-axis, and this axis over here will be time t. What the units are will depend on the problem. It could be seconds, minutes, what have you. The intercept here, this is ln of A naught. If you have ln of A naught, and you would say you want to know what A naught, A at time 0 was, just take the exponential of this, of the number there, and you'll get that because the inverse function of the natural log is the exponential function. The slope m is equal to minus k, meaning if m was, for example, minus 2, then k would be equal to 2. And if this units here were seconds for for t, that means K would have be inverse seconds in terms of units. This will have no units associated with it. This is dimensionless. This has no units. The ln of AT will have no units. On the other hand, this will carry units of time, typically seconds, sometimes minutes, what have you. These are great forms. There is another form that's convenient. You could take this is log base E, so by taking the exponential of both sides, you get AT over A naught, A0, is equal to e, the exponential function, minus kt, which you can rewrite this as a at time t is equal to a naught e to the minus kt. This is convenient as well. So I would say the three forms of this equation that are useful is this form. You can use that. If you want to plot it as a line, you can use it in this form here. And sometimes if you want to know what the concentration of A is, you have initial concentration given, and you know how long it is, and you have the rate constants given, or you can figure it out. This is convenient to use as well. And so this would explain why when you make a plot of the concentration of A, put an A sub t versus time, and you do not plot it logarithmically, you plot it as the concentration itself, it has this exponential decay type behavior because you have this exponential function. And so that's useful. So I'll let you get a good look at that. That is first order behavior in terms of the math. Let's work a problem. You can refer back to these equations because I do have to write some more stuff on this board. Feel comfortable manipulating these equations. This will require college level algebra skills. We will not use calculus in this course, but again, if you do know it and you want to see where the rudiment equations come from, have at it. I've worked that out for you, at least some of it, in my notes. So let's use these equations as needed. One thing I want to point out for the first order process is that we have this form here, ln of AT over A naught is equal to minus KT. We have the concept of a half-life. So the half-life, let's say you go from 1 molar to a half a molar, you've decreased the concentration in half, we call that a half-life. I'm going to put T1 with a little subscript 1/2 to represent a half-life. Similarly, if you went from 1/2 to a quarter, that would be another half-life. Now, whether that number is the same or not, let's see if that's the case. So let's set this up algebraically. So just to get a general form, a half-life, if you have initial concentration A sub 0, that's your concentration at time 0 when you begin the experiment. For half-life, that would mean that this would be, A sub t will be A sub 0 divided by 2 equal minus k. And I'm just going to call it T1/2 to denote that we're talking about half-life. The A sub 0s or A sub naughts cancel out. It's giving you ln of 1/2 is equal to minus kt1/2. By algebra rules, that means ln of 2 is equal to not negative kt1/2, but kt1/2. I'm using that algebraic property that ln of, I'll just say, 1 over a is equal to negative ln of a. That's a logarithmic property you should remember from basic algebra. So you can solve this out. That you can write this in example. The half-life for a first order process is ln of 2, which is approximately 0.693, divided by the rate constant k. What's important about this to note, this is for a first order process, is that it's independent of concentration. Meaning, whatever the time is, let's say it's 1 second to go from 1 molar to 0.5 molar. To go to 0.25 from 0.5 is only another 1 second. To go from 1 molar to 0.25 molar would be a total of 2 seconds. If you took this and you went to 0.125 molar, half of that, that would be another 1 second. So that's a property. It's independent of, you can think of each step as starting over, if you will, but it's independent of those concentrations. So that's an important result. I'll put a star here. If I give it to you on the exam, that's fine. If I don't, you either know it or write it down. That's important information. So let's continue on with first order. There's a lot to this. I'll make separate video for all of these, maybe another video on first order if we need to, depending on how far we go and how much memory I have on my phone here. I'm doing this all on my phone. So let's set up a problem. Let's say we go from 0.100 molar. We're curious if we have some reaction in this form, not worried about the chemical identities, to going to 0.025 molar. So when I'm looking at this, so let's say we know that I'm telling you at a certain temperature, because K is actually a function of temperature, it's 0.100 inverse seconds. Now, on a test, a lot of times what I'll do is I don't say the reaction's first order. I'll give you a rate constant, I'll put units on it, and that's telling you it's first order. That's a big test hint for not only me, but when you take tests like the GRE, MCAT, the dental test and so forth. These are the type of things that they like to see if you know basic chemistry. So first thing I'm noting is that this is 2 half-lives. It's like going from 0.1 to 0.5 to 0.25. It's 2 half-lives, and these are all molarities. So I can see that. So one of the ways I can do this is that I can say the half-life is ln of 2 divided by 0.100 inverse seconds. That's going to pull my seconds up to the numerator, and that's to 3 sig fig, 6.93 seconds, because again, inverse seconds in the denominator gives me seconds. We have to have time and units of time. And so 2 times that is equal to 13.9 seconds. So that's a perfectly good way of doing this problem. That would be the time to go from 0.1 molar to 0.25 for this first order process would be 13.9 seconds. Do you have to do it that way? No. If you forgot that way, you can readily do it for the same rate constant, same problem, like such. So what you could do is say, for example, ln at time t is going to be 0.25 molar. The molarities will cancel over the initial concentration, so I'm using that logarithmic ratio form that we had from the prior board, and that's equal to the rate constant, K, divided by T. Solve this out for T, do your algebra. T is going to be -1 over 0.100 inverse seconds, which pulls the seconds to the numerator. Ln of 0.25 over 0.100. This is -1/4. This is ln of a quarter, which will be negative, and this is going to be a negative times a negative. Gives you a positive. If you don't come out with a positive, you know you did something wrong. So T here would be the same number, verify it, 13.9 seconds. So I get the same answer, meaning you can always use a form of the integrated rate law directly. You're not constrained. You can always use the integrated rate law. With first order, the half-life calculations for some problems end up being just more convenient. So let's take the same chemical system, same temperature, so we have the same rate constant, same structured equations, and do another question. So what if we went from 0.100 molar to 0.0350 molar in A? Now this is not a half-life, and what I'll do, some people will do, well, it's kind of a little more than a half, a little less than a halving. No, you can do it directly. There's no reason to do an estimate based off the half-life. Do the same type of equation before, set it up in the form of the logarithmic ratio is equal to -kt, and then solve for t, and you'll have it in the form of t is equal to -1 over 0.100 inverse seconds times ln of what it is at time t, 0.0350. over 0.100. This will be less than 1. We have a negative number here. So what we'll have is it ends up being 10.5 seconds. 10.5 seconds. Another problem we could do is with the same chemical system, so I'll let you get a good board there before I erase it. I try to stand out a screen so you can watch as much of what I'm doing as possible and try to back out so you can get a good screenshot. I verify I can, with my bad eyesight, see everything on my phone screen. Sometimes I have to enlarge a little bit, but it looks like everything's good. What if we want to know what the concentration of A is after, let's say, 8 seconds of time? So that could be our question. Like, what's the, same system. So in that case, the form of the equation that works nicely is A sub t is equal to A naught e to the minus kt. And remember, when you're in these problems in homework or in tests, A could be nitric oxide, it could be, iodine, it could be all sorts of different things. I'm just using A as an example here just to put a letter or something. It could be a chemical species. Don't sit there and say, well, it's not A. It's, I've had people come up to me and test, say, I don't know about nitric oxide. I'm like, it's first order. That's all you need to know. And so, after 8 seconds, let's set it up. Well, I said that it was 0.10 molar. We have the exponential, and then we had k happen to be the same number, 0.100 seconds minus 1. And then the time, 8 seconds. Here's a key point people tend to miss up. Let's say I said 2 minutes or something like that. Well, then you're a minute. Convert minutes to seconds or convert the inverse seconds to inverse minutes. The units have to match here because you want seconds, the inverse seconds and seconds to cancel. You have to have this, what you have inside the exponential has to be dimensionless, has to have no units. The units are carried by the coefficient in front, the initial concentration, and provided I did my calculations correct, always check it out, make sure I didn't do a typo or a write-o on the board, but I end up getting 0.0449 molar, which makes sense. Compare this to the actual half-life, which is pretty close. The half-life's about 7 seconds-ish, so this should be a little bit less than 0.05, and it is. It makes good sense. It's slightly overshooting the half-life. So again, no reason to estimate. We have ways of calculating. So on that note, I think that was a good video. You learn a lot of steps. You have to work these on your own. I would almost guarantee on any test I give for this course, no matter if it's a summer or a main semester course, I ask these type of questions, both graphic analysis as well as, so being able to interpret the plots, which you can pull off of it, the units of K, and then when you see a problem and it has inverse time for a rate constant or a plot that looks like it's a first order process, it's a logarithmic y-axis and a time-based x-axis, if you want to call it that, and it gives you a straight line going down. That's characteristic of first order. You know to set up first order math. You know how to take the equations I give you and manipulate them algebraically if you need to. I allow you, if you can come in with a sheet of paper, you should be able to manipulate them and write down different equations, whether you have them written down or not. But feel confident with the algebra. Be able to solve these out in all the ways that I'm doing it. Half-lives for concentrations that are halving or not, and also how to figure out what A is, or whatever the reactive species is, as a function of time using the other form with the exponential built in. So that's first order. We'll go on to, I don't know what we'll do next, either 0th or second order next. It really doesn't make a difference. On that note, it's been a good video. It's a little longer side, but that's fine. This is important stuff. So take care. Maybe I'll make another video later, depending on how long this takes to upload.